Now we will move to another one, that is called lubrication and surface roughness in machining processes. In the tribology, surface roughness in machining, we have seen chip tool tribology, we have already seen in the previous class, and the tool workpiece tribology and sticking and sliding zones we have seen up to this one. And we are going to see the types of lubrication, why the lubrication is required in the machining process, why only the lubrication from the point of tribology is most important. That all we will see here, and followed by the surface roughness mostly. In this class we deal these two things. Okay, so types of lubrication, the lubrication and surface roughness in the introduction to surface roughness, as well as surface roughness in the machining process. Okay, that's what we are seeing here. So you can see the types of lubrication. First we will see this one. Okay, so we will look into two aspects whenever we talk about the need of lubrication and types of lubrication. See, I am talking about lubrication. Okay, so I am not talking about the cooling aspect. So why I am talking about the lubrication is whenever there is a friction between the workpiece and tool, normally there is a frictional heat development and all those things. If you have a lubrication ability, or if you are lubricating properly, that friction won't come. Assume that if I have a workpiece if I have a tool here, if the proper lubrication is not there between flank surface and the final product that is coming out, okay, if the proper lubrication is not there, what will happen? The wear of tool will takes place. Okay, that means I am talking about the workpiece and tool interface. Okay, if the lubrication is provided in the chip tool interface also, if you are providing in this two also, what will happen? So the frictional heating that we have seen in the previous class will be done. What I mean to say is that there are two types of heat because of the plastic deformation that is taking place at severe level, that is the main cause of the heat generation. At the same time, frictional heat between chip tool as well as tool final product also will takes place. You can eradicate the second one by providing the lubrication. Okay, so need of lubrication, if you see the need of lubrication, heat generation by the shearing, that is what I am talking about. Shearing, plastic deformation, severe plastic deformation, this is a major culprit which generates the heat, that by conversion of mechanical energy into the thermal energy. The second one is heat generation due to frictional heating, that is what I was talking about, which you can eradicate by the action of lubrication. Okay, the second one which is given here, you can eradicate this by giving proper lubrication. You can avoid this by proper lubrication action. Okay, so if you can provide proper lubrication in chip tool interface, you can reduce the frictional heating. If you can reduce this region proper cooling, you can put a jet here and you can throw here. At the same time, you can also put a nozzle here and you can send here. So these are the two options where you can overcome the heat generation by the friction. Okay, you cannot overcome by the heat generation by shearing, that is plastic deformation. You may not, but however you can control this frictional heat. Okay, at the same time, coming to the tribological aspects which you have seen yesterday also, this is the frictional heat and the temperature that is developed. See, if I can put a lubricant on this track, what will happen? The temperature that is showing on this column, which is showing in the column, you can reduce. Okay, so the blue color shows lower temperature, the yellow color shows slightly higher, orange color and red color shows slightly up, so you can reduce this one. Okay, on an average, the bottom line of this slide, what I want to tell you is, if you can put the proper lubrication into the machining zone in the flank surface as well as the rake surface, the best thing that you are going to get is you can reduce frictional heating, that is the heat generation, frictional heating you can reduce actually. Okay, so that is the what the bottom line of this slide is concerned. Okay, this is about the need. And another one, how to understand this is, if you have seen in the previous class, what I am talking about is AR is the real area of contact as well as A is the apparent area of contact. Okay, if you have seen, so if normally if I want real area of contact, my aim as a mechanical engineer or a manufacturing engineer, my aim is that real area of contact between my tool chip should be 0 or minimal. That means that I am sending a lubricating layer or a cutting fluid that in between these two surfaces. That is what I want. Okay, so here the real contact area is these points, but still I don't want these points also. So for that purpose, normally lubrication is used. Okay, so if I am using a lubrication, how? So if you can see this real area of contact, these are the real area of contact, but still I don't want this. So that is what my ambition as a manufacturing engineer. If I want to reduce the tool wear on the rake surface as well as on the flank surface, I don't want the contact, but on the flank surface at the cutting edge, you will always have the contact because it is the portion that involves in the machining operation. So in terms of crater wear and in terms of rake surface, what I want is I want completely two independent separated by a lubricating film, whether it is a thin film, whether it is a thick film or anything. Okay, that is what I want. If it is a thick film, that is well and good. If it is a thin film, still it is good. Okay, so now we will see about what are these films and all those things. Okay, lubrication. Okay, lubrication in machining, the process of lubrication helping the surface to separate. Okay, this will separate the surfaces, that is called, one is a tool surface, another one is a chip surface or the flank surface, reduce the resistance of the interface. Okay, so that it will reduce the resistance in the interface. Okay, so to produce the fluid pressure sufficient to prevent the opposing asperities from touching. That means that I am sending, in the previous slide if you have seen, if I have to send this in between two surfaces, my aim is always to separate these two. That is what I am talking about. Okay, so the viscosity of fluid decreases with the temperature. Normally, if you increase the temperature, this is the temperature, this is the viscosity of your, normally it will decrease. Okay, because the viscosity will go down. If you see in terms of the polymer, if you see in terms of gels and all those things, what will happen? If a semi-solid polymer is there, if you increase the temperature, what will happen? The viscosity will come down because the intermolecular force of attraction between these polymer molecules will go out. Normally, the cutting fluids these are also petroleum based products where these are also can form the small plasticizer like of polymers. So this is the same analysis that you can see here. Okay, so higher viscosity index, the less change in viscosity. If the viscosity index is high for a particular fluid, what will happen? The change in viscosity normally will be less. That is what I say. Okay, the properties of the lubricant, as I was telling you, if as a manufacturing engineer, my aim is to send the cutting fluid or the lubricant between these two surfaces. If I can send between these two surfaces, that is good for my machining, so that the tool wear don't come. This is the crater wear that is coming on this one, that is called, this is a tool, this is a chip basically. Okay, if I can send a layer of cutting fluid which is dominated by the lubrication, I can overcome the frictional heating between chip and tool. Normally chip carries 80 to 85% what I was telling of the heat generation. So already workpiece is carrying 10% approximately. So the heat conduction takes place like this. At the same time frictional heat also takes place. If I can put a lubricating film, what will happen? The film, as you have seen in the previous slide, it will absorb the temperature and become low viscous. Okay, so if it is low viscous, better flowability will be there for the lubricant. At the same time, it will have a convection heat transfer between tool and lubricant from one side, chip and lubricant from another side. So it will act as a barrier which takes the temperature or the heat that is generated in between the tool chip interface. Okay, that is what my ambition in using the lubricant. So the properties of the lubricant can be considered. Normally density should be optimum. It should not be too dense. If it is too dense, what will happen? The cutting fluid cannot go. That's why normally the mineral oils are clubbed or blended with water so that the viscosity will come down. So vapor pressure and viscosity index, thermal stability and oxidation stability should be better. So that it will have a good properties. Okay, at high temperature, when the lubricant viscosity is very low, the surface may touch, leading to friction. Okay, there is another problem. Okay, whenever if I am using a cutting fluid, if the temperature is very high, what will happen? The temperature is very high, so as you have seen, the viscosity will come down. In the previous slide also you have seen the temperature, viscosity, okay, it will come down. If it is coming down, what will happen? There is a chance that mating surfaces will come together and again the wear takes place. So it should have proper density. Even though you are giving high temperatures, it should not become like a too thin fluid. Okay, so that's normally companies will take care of these things, and you should rightly choose your lubricants for your application. For example, if you are expecting two materials, that is, but assume that you want to choose a carbide tool versus any mild steel or any slightly better than this will AISI 4340 or something, what will happen? You have to choose what will be the cutting fluids based on the temperature expected from the literature. You see the temperature, what is the temperature that is reported in the literature? Can this cutting fluid can sustain my temperature? So that the viscosity should not go down completely and mating surfaces will come and destroy the tool. It should not happen. Okay, so one should take care about this. So types of lubrication, if you see, one is a boundary lubrication, second is a mixed lubrication, and third one is hydrodynamic lubrication. Okay, these are the three lubrications are there. Okay. Why I am talking about these lubrications? I need in the two zones, flank surface and workpiece. This is called workpiece region. This is chip. This is anyhow tool is there. Okay, I need to lubricate these regions. Okay, this is the one region. This is the second region. Okay, let me erase this one. This is the region 1 and this is the region 2. Okay, so I want to lubricate these regions. If I can properly lubricate these regions, the temperature going into the tool will be enormously reduced. Okay, so for that purpose we have many types of fluids, that is called shear thinning fluids, Newtonian fluids, shear thickening fluids, and Bingham plastic fluids. These are the fluids. Okay, so how do we define all these fluids is one thing. Normally Newtonian fluid, you will have always a straight line, so shear rate versus shear stress, obviously it will be unity type where n equal to 1. If n is less than 1, it is a non-Newtonian fluid having shear thinning nature. What do you mean by shear thinning nature? For example, to understand what is shear thinning, what is shear thickening and all those things, I have to explain you the rheometer. So if I have a rheometer, this is the top plate where it can rotate. Okay, so bottom plate will be there. I am just having a fluid film here. This is the fluid film, and you have a bottom plate, fixed bottom plate. Okay, so this is a fixed bottom plate. I am putting a fluid in between and I am rotating the top plate. Okay, so the top plate is rotating. What will happen? I have a fixed bottom plate. In between I am putting my fluid, whatever the fluid, I am just my rotating the top plate. As the shear rate increases, what will happen? If the viscosity goes down, that is called shear thinning fluid. If I am increasing the rotational speed of my top plate, that means that my shear rate is increasing. Okay, so if I am increasing the shear rate, if the fluid viscosity is increasing, that is nothing but shear thickening fluid. Okay, that is the difference about the shear thinning fluid and shear thickening fluid. If nothing is happening, it is a Newtonian fluid. Now what is a Bingham plastic fluid? Normally Bingham plastic fluid, if you see here up to this portion, there is no change. That means that this is called yield shear normally. Okay, initial. So for example, if you take the paste, if you just squeeze it, if you put it like this, assume that this is a tube, paste tube, just if you put like this, it may not come on its own. You have to press it, squeeze it, until unless you don't give certain press on it, it won't come. Okay, that is nothing but this one, the minimum. You have to give minimum so that the flow starts. That is nothing but the Bingham plastic fluid. Normally they will say Bingham fluids. Okay, so this is about the different fluids which are used in the lubrication. Okay, in terms of whatever the lubricants the petroleum industries are giving us. Okay, Stieback curve is the normally explained curve in terms of lubricating in bearings. The same analysis you can take into the metal cutting also. Okay, assume that I have a chip tool interface. Okay, this is the interface that I am talking about. Okay, this interface I am talking about. This interface can be anything, whether it is a boundary lubrication, mixed lubrication or hydrodynamic lubrication. That now I am going to talk about whether how to achieve in this one, what is the types of lubrication that are going to take place in this region. Okay, so in a boundary lubrication, if you see the boundary lubrication, this is the boundary lubrication. That means this is the one. Okay, boundary lubrication, what is lubricating is here the dominating is the metal to metal surface. Okay, if I am telling about tool versus chip, so dominating thing is my chip asperities are in contact with my tool. That means I am talking about completely the sticking region. Okay, there are two regions of the tribological regions in the machining surface. One is a sticking region, another one is a sliding region. So I am talking about the sticking region. Okay, so next comes partial contact, that is called mixed lubrication. Only big asperities come in contact, but there is a thin film of lubricant layer will be there, that is called mixed lubrication. Okay, so you can see here big asperities are in contact, that means there is a variation in surface roughness on the tool, which we will see as well as we have seen already in the previous class. This variation of the tool, the high peak surface roughness of the tool will have contact, and remaining portion you will have a thin film of lubricating layer. Since you have a contact of lubricant with the both the surfaces, at the same time big asperities are there, that's why it is called mixed lubrication, asperities plus lubricant. In the third one is hydrodynamic lubrication, which is nothing but you have a thick film of lubrication where the asperities don't come. You can see here completely lubricant film is there. Okay, this is about the hydrodynamic lubrication. Anyhow, we will see the strike-back curves, different ways. Some people explain in a different way, some people will explain in a different way, and all those things. Here you can see the same thing, coefficient of friction, how it will vary. Here the boundary lubrication normally will have a dominating effect of the surfaces to surface. Assume this is the chip surface, this is the tool surface, cutting tool basically. So because the chip is moving at velocity, there is a relative motion between two surfaces where the dominating is between chip as well as the tool. Here both lubricating film as well as the asperities of the both the surfaces, here dominating by the lubricating film. Okay, you can also see on the friction coefficient how it will drastically goes down and the film thickness increases. Okay, both are converse to each other. If you see the coefficient of friction in the boundary lubrication, because of the mating surfaces, two mating surfaces are there, because of the two mating surfaces of chip as well as tool, it will be very high, coefficient of friction is very high. Whenever the mixed lubrication comes, it will drastically comes down, because you will have completely a small portions of the nanometric asperities which are very big will only in contact, but thin film will be there. So the transition between solid to solid, 99% thin film contact gradually increases, the film thickness gradually increases if you are moving from boundary lubrication to hydrodynamic lubrication. Here it is a thin film, here it is a thick film. Okay, the transition of the thin film, here the thin film is minimum, here it is minimum, here it is maximum. Okay, this is the thickness that is normally observed at the start of hydrodynamic film. That's why the coefficient of friction enormously decreases, and at the same time you can see the film also thickness is gradually increasing. If it is increases, that is good. So hydrodynamic film normally it will be have slightly increases because viscosity will come into picture and all those things. Okay, that's why this lubricating film is required. As a manufacturing engineer, I want the hydrodynamic lubrication between my mating surfaces, that is tool and workpiece, or chip and tool. I want it, but practically it is not possible. Most of the time what you are going to achieve is mixed lubrication. Okay, so if you see here in the metal cutting operation, if you normally see in the sticking region and the starting of sliding region, and this is end of strike-back curve normally explain the three things: what is the boundary lubrication, mixed lubrication, and hydrodynamic lubrication. Sticking zone, obviously, as I was explaining again and again, it has a metal to metal contact, so there is nothing like fluid can not enter into that region because solid to solid contact is there. In the sliding region, there is a relative motion in the sliding region because of the fluid flow, the lubricant that is sent at high pressure or it will occupy some of the regions, and still there is asperities come into picture. So asperities plus lubricating film will be there, that is about the start of the sliding region and end of the sticking region. Okay, coming to the sliding region ending and to the free end, you will have always the hydrodynamic lubrication. But as a manufacturing engineer, I want to increase the pressure of my pump so that I can inject into the sliding region, entire sliding region. I want to make the sliding region like hydrodynamic lubrication. At the same time, I also want to make the sticking region as minimum as possible by penetrating my lubricant or cutting fluid into the region of sticking region. So as a manufacturing engineer, I don't want a sticking region, but practically it is not possible. So only thing is that I can minimize the sticking region. So now if you see the tribology of the metal cutting, what are all the things that if at all you want to study more about this tribology and all those things, you can go through this tribology of metal cutting by Professor Astako. He is one of the great professors who normally explain the practicality of the metal cutting processes. Even though I have not taught completely of this book, I just have the glimpse of these books. So if you want more details about the tribology of metal cutting or mechanics of metal cutting and all those things, you can follow these books. Okay. Now we are moving into the surface roughness in the machining process. So the surface roughness is the final thing that everybody see on a product. Assume that I want to see a particular product, so I will see how beauty this product is. So how do you explain? You have to explain from the point of its surface roughness. Surface roughness give you good life, at the same time good aesthetic appeal to the product and all those things. That's why a customer want a good product. Suppose if I want to give a customer a good product, you have to give him a better surface roughness. Better surface roughness means you have to produce low surface roughness. That means that better surface, higher surface finish. There is nothing quantitatively high surface finish. Normally qualitatively you can say the surface finish, but whatever you can measure is the surface roughness. Okay, so the surface roughness is one of the important, but for roughnesses there are finishing processes also. To not waste much production time, people will also use the machining processes itself give the better surface roughness. That means that low surface roughness by decreasing the feed, increasing the speed, decreasing the depth of cut and all. There are some parameters one has to play. Initially you cut with more depth of cut and feed, gradually you reduce it with high speed and all those things, having a better tool. This is what one has to do. Okay, let me come into this one. So we are coming into the surface roughness because we have done the types of lubrication and other things. Okay, so just now we have completed this one. Okay, if the surface roughness is the only factor that you look at a product, probably not. Okay, you also need to look many things, that is such as surface metallurgy and all those things. That's why nowadays concepts are coming with surface integrity. Okay, surface integrity does mean it is deals with the surface roughness, that is nothing but the surface morphology, at the same time surface metallurgy. Okay, not only you see the surface roughness, you have to also see the metallurgical aspects of the metal that is finished. Okay, assume that I have a product which having very good surface roughness. That means that a very low surface roughness. Assume that it is having a heat affected zone. That means that recast layer, heat of thermally destroyed layers, you cannot use it in whenever you do the machining operation. You should take care that there should not be more temperature in the machining region, so that there won't be any burning marks on the product. Even though surface roughness is very good, if your burning marks are there on the surface, that means that that may not be possible to put into the practical application. That's why you should look at surface integrity of that particular product. Okay, the surface roughness, what we will look at it is surface roughness and surface metallurgy. That's because we are dealing with only mechanical aspects, so we deal with surface roughness mostly. But however, just I gave you the glimpse what is the requirement of surface metallurgy. Okay, introduction to surface roughness we will see, then we will followed by the surface roughness measurement, practical parameters that affect the surface roughness in the machining. Just we see at the same time we see the surface roughness in various machining operations we will see. Okay, surface roughness on the tool, how it will affect surface roughness on the workpiece and all those things. Okay, till tool we may see today. So introduction to the surface roughness. The surface roughness, if at all, if we have a 3D surface, if we just see, there are three things. One is profile roughness, waviness, and roughness, surface roughness. Okay, so we will, for a particular surface, there are some other things that I will come, which is lay, what is meant by flaw. Okay, so what do you mean by lay, what is meant by flaw, these are all things will come later. If I have the surface, if I just want to measure the surface in a 2 dimension, this is a 3-dimensional surface, 3D surface, and I am measuring, I am putting a line across this one and I am measuring the surface roughness. Okay, so whatever the original profile that I am going to get here is profile roughness. This is called profile roughness, profile surface roughness. I can say, sorry, let me not confuse much. So it is called profile roughness, and you can divide this profile roughness into two things. One is waviness, another one is surface roughness. Okay, if this high amplitude thing is waviness and this is called roughness, that is called surface roughness. Okay, so that means I have profile roughness, I can divide into waviness, which is, if I see a profile roughness, this is like this. Okay, so the which you can divide into two things. One is a waviness, and what the roughness things are there on which are superimposing on the waviness is nothing but the surface roughness. Okay, so this is about the three things. Okay, now we will come to what is a lay. So lay in the previous one, which is called, it is a predominant direction of the surface roughness. Okay, so our predominant surface patterns caused by the machining process is nothing but the lay. Okay, flaw, normally flaws are nothing but, if you see here a flaw is there, this is the flaw. Flaw is nothing but the scratches, holes, cracks, ridges or hollows that are presenting on the surface, which are not as a part of machining process. Okay, just we want what is the lay of machining process. The lay is nothing but the predominant surface, predominant direction of the surface. Okay, it may differ from machining process to machining process. In a turning process, you may get the circular pattern, that is feed marks. In the grinding operation, you may get a straight line surface pattern, that is what is written here. The roughness height, roughness width, waviness width, these are all the things are there. However, you can represent the surface roughness in terms of these things. Normally the surface roughness will be explained like this. Okay. So the first thing is surface roughness height, here it is mentioned. Surface roughness width is this one. This is the direction. Normally this will show the perpendicular direction, and the waviness width as well as waviness height. This is the height and this is the width of the waviness. Okay. So these are the things that you represent in this one. Okay. Experimental measurement, normally how do you measure? So there are two things. If you see few years back, like 10 to 15 years back, we used to have the contact type of surface profilometers. For example, pocket surf is the one of the thing that is developed by Mar, is the one of the companies. So later, if we surface analyzers are the federal surface analyzers, if at all I want this pocket one, it is a portable one, you can take to any place and you can just assume that I am doing a lathe operation, is a big rod. If I want to measure the surface roughness at different levels, just you have to put on the top surface and you just measure it. Okay. So in some surfaces like grinding and all those things, you can bring the workpieces and you can use the surface analyzer, which is shown here, federal surface analyzer. Just you place your workpiece here and you just move it and it will give you the surface roughness. Okay. Here also probe is there, just it will reciprocate and it will give. Okay. How it will give the values? Normally if you see pattern, the evaluation length is the length of the travel of my contact profilometer probe. Okay. So it will move complete distance. How? There are different ways you can specify the evaluation length, or normally you can give the sample length. There is a standard procedures are there. I am dividing into 5 zones. In 5 zones, first zone plus 3 zones plus last 1 zone. Okay. The first zone and the last 2 zone, it won't consider for any surface roughness measurement, because it is starting, the probe is starting initially from the 0 velocity and it is going. At the same time, in the last one, it has to come to 0, because the velocity is there, certain velocity, and it is coming to 0. Okay. So that's why first and last it won't consider, it will consider the 3 things and normally it will give. That is what some of the books explain. And many non-contact, nowadays people work on the non-contact type surface profilometers. Okay. So the surface roughness, it is a numerical assessment of surface roughness, can be carried out by the number of ways. One is the numerical values are obtained with respect to a datum. Okay. So there will be a datum, normally according to that normally you will take. So the following 3 methods are there. One is peak to valley method, and average roughness method, and bearing area curve method. Okay. So anyhow, since we are talking about the surface roughness, just we talk about only the roughness. So if you see here, so this is the mean, the surface. Just you make it, I have a random surface on which my probe is moving and it will give me the value. So what is going to happen inside? Okay. That will always will be a doubt in the surface roughness. Assume that I have a surface on which my probe is moving and it will give you certain value. Okay. Assume that it is giving micrometers. How it is going to give? Okay. Now it will draw a mean line where the area above the mean line is equivalent to area below the mean line. Okay. There comes the mean line. Okay. So now I have a surface, this surface, for example, just I am drawing up to this one only. So once it completes, what will happen? It knows the area above the curve equal to area below the curve. So it draw a mean line. With reference to that mean line, it will give all the values. Okay. So normally whatever you measure is average, that is called CLA value, that it is how do you measure, I will explain you. Another, okay, this is the RA, where RA is nothing but the central line average value, okay, it is called CLA. RA is nothing but central line average value, okay, central line average, CLA. Okay, how it will be do? Normally RA equivalent to, here whatever is given, the same thing I am writing, 1 by L integral 0 to L mod y of x into dx. Okay, why I am taking mod because values normally will come in the negative direction. So if I take mod, basically I am going to take all the positive directions only. Okay, RQ represent the root mean square value. Okay, so the difference where you will get between RA and RQ is if the surface roughness is very high, in that circumstances the square root values will go up and RQ normally slightly higher than RA value. That's why most of the countries will follow RA as their standard parameter for the surface roughness. Okay. Okay. The other parameters normally if you see RP, that is mean line to the maximum peak, and RV mean line to the minimum value, that those are the two things. RT is nothing but the maximum peak to minimum value, that is RP plus RV. This is maximum peak to minimum value. So the parameters normally are the responses, surface roughness responses that one can observe is responses are RA, which is central line average value, RQ, that is root mean square value, and RT, which is nothing but maximum peak to minimum value. Okay, these are the three things that one can consider. If somebody is doing the research in the metal cutting area, so you can consider this on the workpiece with respect to feed, with respect to depth of cut, and with respect to type of cutting fluid and the speed of your workpiece, that means workpiece rotational speed or cutting speed. You can vary, it's one of the good parameters because always the customers want the better surface roughness. Okay. Okay, the surface roughness, how do you measure? Normally by inspection method one, another one is direct measurement one. Okay, so but the problem with the inspection method is that this is assessed by the observation. Okay, by observing you can tell this may be this. So it is basically a qualitative thing. Okay, I mean to say I have a product. Okay, this product is good. I cannot say this product is the surface roughness is 1 micron, but I can say it is good. See, that means I am comparing with respect to some other product which is there. Okay, it is a qualitative statement. I say I am a good person. That means that I am comparing to certain person and I am saying that I am a good person. Okay, so I am a bad person. So this is just a comparison. Okay, that is what the qualitative assessment, whether for a particular person is a good or a bad, it is a qualitative assessment. I cannot say 10% good, 10% bad or something. Okay. The texture of the surface is tested and compared with respect to the specimen of known surface roughness value finished by the similar process. Normally what it will be done is it will be tested by the with respect to a product that is already done by the same machining process. If something is there with respect to the turning operation, you have taken a newly turned sample and I have to say whether it is good or not good with respect to a masterpiece that is done by the same input conditions of that machine. Okay, then I can say whether it is good or not. It is qualitative too. Okay, but this is not reliable because the comparison may not be produced by the similar technique. Okay, sometimes a product is developed by the turning process, sometimes a product is developed by some other process. If at all you want to compare, then it will lead to a misleading. That's why you have to always go for the quantitative measurement. Okay, so inspection by comparison, normally visual inspection, touch inspection, scratch inspection, microscopic inspection, surface photographs, micro interferometer, wall surface dynamometer, reflected light intensity. These are the things normally you can use. These are the techniques normally in olden days people are using. Okay, nowadays I don't think these are still exist. For a qualitative assessment in a mass production, you can go ahead with these processes. But if at all you are looking for a nano surface roughness or some these type of roughnesses, this process of inspection may not work. Okay, to go to the better surface roughness measurements, there are quantitative analysis methods that are called direct instrument methods. Okay, this determine the numerical value of the surface finish. Directly it will give you whether it is a 1 micron, whether it is a 10 micron or something, it will give you. Okay, where nowadays it will have a direct probe method where stylus will be there, stylus will reciprocate, which you have seen in the measurement technique where evaluation length and all those things I have explained. So the probe will reciprocate on surface, like this is the surface, the probe will be there and it will reciprocate and it will give you the quantitative value. That's about this method. Okay, so the surface profilometers is there, profilographs are there, Hobson surface is there, and surface meters also there. However, I will go through only few things. Okay, the same thing previously you have seen. So this is a pocket surf. What I want to tell you the difference between the previously the same slide and this slide is, this is the stylus method, where is the probe method, direct contact is there. Okay, so this has its own limitation. If the probe, this is the probe, normally this is the probe, you can see a small one is there, here also you cannot see the probe. This will reciprocate on the workpiece and it will give the value. Okay, so this is about the contact type of surface roughness measurement. Okay, so but problem with this one is it cannot give me the three-dimensional surface roughnesses and all those things. At the same time, it may not give me in the nanometric level. It can give, but may not be that much accurate. For that purpose, there are 3D surface profilometers where non-contact type of surface roughnesses are there. You can see the Taylor and Hobson, where this is a eyepiece, where you can keep your workpiece here and you can just put the, it works on the interferometry principle. There is a white light interferometry method it will use. Just it will pass and it will receive the, and it will give you the 3D view of the surface roughness. You can see how beautifully the surface roughness is, and from here, if at all I want to measure a line scan, if I want to measure here, I can take a profile, like it will give me a profile like this. If I want to measure here, since the peaks are dominating here, I can get a profile like this. Since peaks are there, I will get a profile like this. So I can get 3D profile, as well as from the 3D profile by putting a line scan, I can get the surface roughness in a 2D across that line. So that is the beauty about the non-contact type of surface roughness. Okay, this is the 3D image where you can see here 3D image. You can get the 3D average surface also. If at all I don't want a 2D, a line scan, I want complete area what is the surface roughness, still I can get it. So that is called, normally they will, some of the people they will take, indicate about SA, that is surface average surface roughness. So normally you will get, if at all I want, I just take a 2-dimensional of this one. Okay, this is like a 2-dimensional where average surface roughness is done. Okay, so typically how the surface roughness in the lathe turning process look like is this one. Okay, so representation of surface roughness, how to represent the surface roughness, whether it is milled surface, whether it is a turn surface and all those things. How do you represent in a practically? Okay. So, this is this symbol and interpretation. Okay. This normally whatever here it is that it is a parallel to the plane projection. Normally it will give you the parallel surface. For example, it is shaping. Okay. Perpendicular to the plane projection, this symbol shows perpendicular to the plane projection. Okay. If my surface is there and I am doing like this. Okay. So, this is the perpendicular surface, and crossed, this shows the crossed one. Normally if you see that crosshatch pattern in the honing process, you will observe multidirectional. M stands for multidirectional and C stands for circular toward the center. You can see here. At the same time, R represents the radially relative to the center of the surface. Okay, this is the radial surface. This is the circular one. This is the multi-direction. This is the crosshatch pattern, and parallel and perpendicular. These are the interpretation of the symbols in the lay. How the predominant direction of surface roughness that one can explain. Okay. So, normally the surface roughness in a turning operation in micrometers, you can see here. These are the ranges 2 to 2.5 to, this is the old values, very old, we have taken from the old book. So, these are slightly higher side. However, we in a normal, if you see nowadays with the sophistication of the equipment and all those things, these values can still go down. So, the surface texture or the roughness representation. So, the basic symbols of the surface roughness representation is like this. If you see, the basic symbol consists of two legs. These are the two legs are there, are unequal, which is approximately at the 60 degrees, and this is represented by a thin line basically compared to the baseline. Normally it will represent by a thin line. Okay. So, with this line, now I have this one. So, if at all, if I am removing the material, that means that metal cutting is taking place, this particular portion will come. Okay. The material removal is not permitted, then you have to say it is not permitted by writing a 0 symbol. Okay. With a special surface characteristics indicated, normally if at all you want to indicate, you have to write this one. Okay. So, is as simple, this is the surface roughness representation, basic surface roughness representation. If I want the machining, this one. If I don't want the machining, then I want to remove this one, then I have to write this one. If I want a special type of process, I just want to write this one. Okay. This is about the representation, basic representation. Okay. So, if the values defining the principal roughnesses are added, normally if you are having a surface roughness value, normally if you represent a surface roughness value A, you will represent like this. If you are representing the surface roughness by machining process, you represent this one, and you should not remove any material, but I want the surface roughness value A, then this is the process. This is what you have to explain. Okay. So, if at all some people are writing A1 and A2 instead of A, that means that one represent the maximum limit, another one represent the minimum limit. Normally, if I say a particular product I want 1 micron, nobody can give me 1 micron exactly, because no process is 100% perfect. That is why you always say I want 1 micron plus or minus 0.05. That means that the person can make the component between 0.95 to 1.05 microns. That flexibility should be there. So, I can say here it is 1.05 micrometers, and A2 is minimum limit, that is called 0.95 micrometers. Okay. Or 1.00 plus or minus 0.05 micrometers. That is what I can specify, so that operator can do properly. Okay. So, if at all I want to say that it has to be done, the surface roughness is A and this should be done by the machining process because of this symbol. And the machining also I am going to specify that this should not be made by the turning process or a grinding process, it has to be done by the milling process. So I will also confirm that I want the surface roughness A by using the milling process, that I will explain. So if I am indicating some value here, the indication of the machining allowance where the necessary to specify a value, that is called a machining allowance, this shall indicate the left of the, okay. If at all I am explaining some of the machining allowances, that I will explain in terms of by putting a value in front of the surface roughness, okay. That's overall. If at all I want to mention, how I will mention the surface roughness value RA is this one, the whatever the roughness I want to mention, the production method or the treatment or a coating, assume that I want to do by the lathe, that is turning process, I will mention in place of B, and C is sampling length, okay, and D is direction of the lathe, okay. Whatever the allowance that I want to give, I can give here, okay.